Now we want to start going over to chapter 5 of the book and talk about graph neural networks. We have discussed the shallow embedding based approaches in the previous chapters, and there are many things that are going to be different in this chapter as we go over the concepts related to graph neural networks and their applications. Now the main thing to consider here is that we basically want to propose more complex encoder modules, and we want to utilize any sort of feature vector that is associated with the nodes in the graph as well as the structure of the graph in order to obtain more concise and more informative representations associated with each of the nodes or with the graph. We already know that in different domains, for example, in image recognition, we know that the parameter sharing in the style of convolutional neural networks is the state of the art and is a pretty good and convenient and fit architecture for that task. We know that in dealing with sequences, things such as recurrent neural networks and transformers are very effective. Now the question is, what types of properties should an architecture proposed for the task of dealing with a graph neural network situation have that basically makes it a good and a fit model for the tasks at hand. The first thing we want to discuss has to do with the permutation invariance and equivariance. And that comes with basically paying attention to whether or not the order of the representations of the nodes is important. Now, one reasonable idea, one would say, in dealing with some sort of, with basically applying a machine learning model to graphs, is that we can take the adjacency matrix. So let's say this is the adjacency matrix, and let's say this is going to be ith row of the adjacency matrix A for basically this means 1, 2. Till the number of nodes. Now you can basically flatten the adjacency matrix so let's go over something. So we basically want to propose to use the adjacency matrix as the feature vector characterizing the entire graph. And one thing we can do is that, let's say this is the concatenation operation. We can have this for I from 1 to all of the nodes. And this is going to be the feature vector. And the dimension of it obviously is going to be this. Now, you can basically give it to a multi-layer perceptron, and this is going to give you an output, which is a vector associated with the graph. Now, what is the main immediate problem that comes to mind? The main immediate problem that comes to mind is that this adjacency matrix has basically enforced some sort of arbitrary order over the nodes, and when you are basically concatenating these representations, this means that your feature vector is going to first have the feature associated with node 1 and 2 and 3 and 4. And when it comes to dealing with a graph, it's sort of like sometimes looking at a certain set, and representing a set is not the same as representing a list. And this order and this overindulgence with the order in this methodology that is just proposed is going to cause a lot of problems. Another way of putting it is that this proposed model is not permutation invariant. Now, when it comes to processing graphs and associating features with graphs and things like that, permutation invariance is a critical desired characteristic. In mathematical terms, means that if you have basically a function f that takes the adjacency matrix A, if you have any permutation p, you basically must have this being equal to this. And if it is not the case, you want to have permutation equivariance, which means this. So one of these two must be satisfied. Note that this means that the permutation of the input doesn't impact the output, and this is called permutation invariance. The permutation equivariance means that the permuting the input is going to have the same effect and the same permutation on the output. Considering a graph as a network of nodes, when we were discussing what exactly motivated the architectures related to, for example, graph neural networks, there have been a variety of articles, a variety of perspectives. For example, GNNs are believed to have to do, for example, with the generalization of convolution to non-Euclidean data as differentiable variant of belief propagation, and similar to, for example, the graph isomorphism tests that we discussed before. Now, the main idea has to do with some sort of a message passing, meaning that we want vector messages to be exchanged between the nodes, and we want them to basically allow the representations to be updated using a neural network, for instance. Now let's go over the notation for basically discussing the message passing framework. So first, as usual, you have your graph G, which is composed of set of nodes V and set of edges E. You this time also have a d-dimensional feature vector for each one of your nodes. You want to use this information in order to obtain a dz-dimensional output for every node of your graph. So this is for basically generating representations for nodes, and we're going to also talk about examples of generating representation for subgraphs and for the entire graph. Considering a node in this message passing framework, at a certain iteration or during each one of the message passing iterations, there is going to be a hidden state associated with this node. Let's say this is node U and you're at iteration K, and there is this hidden embedding of sorts. Think about, for example, LSTMs or recurrent neural networks and things like that. So there is a hidden embedding associated with the node that in each stage or iteration of the message passing framework is going to be updated. And the thing that basically plays an important role, the other player in this game that plays an important role in this update, is the neighborhood of node U. Let's take a look at this informative figure in the book. So here is basically how a single node aggregates messages from its local neighborhood. The model aggregates messages from A's local graph neighbors, which are B, C, and D. And in turn, also messages coming from these neighbors are based on information aggregated from their respective neighborhoods, and so on. This means a two-layer version of a message passing model is going to work as shown in this figure. So let's look at the iteration rule for updating this hidden embedding or hidden state associated with node U at iteration K transitioning to iteration K plus 1. So this is the thing that we want to know. The update at iteration K will basically take the previous hidden representation that we had along with some form of aggregation over the hidden states or hidden embeddings of the nodes that are a neighborhood of the node in question. And this can be written, for example, as M because it basically comprises the message from neighborhood nodes. In the context of node representation, the first state could be defined as, for instance, the original input features, and after K iterations, this could be of R, for example, one dimension, and a certain dimension D1, and edge K can be, for instance, the representations that, for example, are on DZ or D2 or whatever. Now the thing is, the aggregate part and update both are differentiable, and aggregate takes a set as input. That means that by default it's going to be, by definition, it's going to be permutation invariant. Now one thing that you see here mainly as a a special point of focus is these node features, or for example, XUs. Now the thing is, in many of the examples, for example, in social media networks and things as such, we are going to have a rich set of features associated with each of the nodes. But if there is no features associated with the nodes, and if only thing that you have as the structure, there are potential options. One is to basically assign a one-hot vector with a node, assign an embedding, or something of that sort. And another option is to basically use node statistics, which is something that was discussed before. So, as discussed before, the main idea behind a graph neural network architecture is basically allowing the message passing framework to help getting information from different reaches of the graph to each node. This means, for example, in the first step of the first iteration, the node is going to receive information, aggregate information from its neighborhoods, and it will be used to update its feature vector. And therefore, after k iterations, we have the k-hop neighborhood of node U to deal with. So in one iteration, you basically have access to your neighbors. In two iterations, two-hop neighborhood. And in k iterations, k-hop neighborhoods, of course. And this is kind of critical because you want to basically have two types of information, message passing, and kind of encode two types of information in your node features. And one is the structural information that has to do with the structure of the graph. And two is basically features and updated features that represent the semantics of the task at hand for the node in question. So we talked about the general update rule for the graph neural networks, and we said that we have this embedding for the node U at iteration k, and this is defined as a differentiable update which works based on the previous hidden state for node U and some aggregation module that takes this set of neighbors of U and their states, and it will basically help with this update rule that we have here. Now the thing is, let's come up with the most basic example for this and kind of talk about what the update and aggregate would be. This was proposed in these two references in the book, and it is defined this way. So in obtaining the hidden representation or hidden embedding for node U at iteration k, you have this function. One kind of important remark is that the number of layers in the GNN are basically associated most often with the different iterations considered in the message passing. Now you can see that for each layer you have this weights, these parameters, and this parameters. Now this is the bias term. We can see the aggregation here is basically summation and then multiplication by this matrix. And the update rule is basically summing these up and passing them through the sigma function. And sigma here is basically an activation function. For example, it could be ReLU, it could be tangent hyperbolic, and things like that. Note that these could be shared between the layers or could be defined individually for each one of the layers. And also note that if you want to write this one based on the message aggregation and update formula, we basically are going to have that the message coming from neighbors is going to be the sum aggregation of the hidden states of the neighbors, and that the update rule, which takes the hidden state of the node U and the message coming from the neighbors of node u is going to be defined as the nonlinearity applied on v self on edge u plus v neighbors on message coming from the neighbors of u, for instance, plus b. To write the same thing, but this time in a vectorized form, and for the entire graph, we are going to have this. So here's the vectorized form of it. Note that edge k is going to be this dimensions in this formula. And this means basically applying the W self on it can change this, but it leaves this one intact, so that when you have the edge t, you again have this as the first dimension. And in here, we can see the role of the adjacency matrix is to basically bring together the nodes representations for the neighbors of a certain node u, because you basically have in order to get this item for ht, you're going to have the corresponding row in the adjacency matrix which has the neighbors, and then you have the edge matrix, and it's going to basically this multiplied by that is going to give you the summation of the corresponding rows, and then you of course will apply the W for the neighbors there, and then you're gonna basically get those outputs. Now, given our discussion, one way to basically simplify these equations is to add a self loop, and then when you're doing the aggregation, considering the set of nodes that are neighbors to you, adding the self loop means you add the u to that set as well, and you basically use the aggregation only, and you get the new result. Now, there's basically pros and cons for this. The pros is better for overfitting, as it is a simplified and straightforward approach. It's kind of similar to the relationship between GRU and LSTM in some sense. And in terms of cons is that the expressiveness of the model goes down, because you cannot differentiate between the messages in the sense of whether or not it comes from the neighbors of u or the u itself. Now let's see what happens to the thing that we discussed before. So in the vectorized format, we had this. Now here, adding self loop means you're gonna basically render these two the same, and will be adding self loop results in this formula. You have the nonlinearity. This time you also have the self loop, meaning that the diagonal elements of the adjacency matrix will become 1 as well, and then you have edge for the previous iteration times WT. And we call this the self loop GNN approach. Now, what we discussed was kind of like the simplest version of the GNN, and now we're going to have to talk about how to improve upon what we had so far. So in the previous approach that was the simplest, we saw that the aggregate function was basically the summation of the nodes in the neighborhood of u over basically the embedding vector associated with each one of them. Now, there is an immediate problem with this, and that is the sensitivity to node degree, meaning that if you have, for example, generally the same magnitude distribution for your nodes, in the next iteration, the node that had 10,000 neighbors is going to have significantly different value range than the node that had 10 neighbors. And this can lead to a lot of numerical instabilities. Now, the simplest approach to kind of deal with that is that when you're considering the message coming from the neighbors of u, you can essentially do the same thing as before. Neighbors of u, v, and edge v of k. I'm going to omit the index k. Yeah, so you take the embeddings for the neighbors, and you divide this to the node degree, which is now the number of neighbors of node u. However, there are some other alternatives that also have found success in the previous research in graph neural networks. One of them is called symmetric normalization, and it is defined like this. So for every node in the adjacency of u, you take the representation of that node and you divide it by this. Basically the degree of node u times the degree of node v, and under a square root. This means that the nodes that have that are neighbors of u and have a lower degree, their message or their embedding is going to be more important in composing the embedding for the next iteration for node u. And we had this before, and the assumption that the nodes that are less connected and that are the neighbors of u are going to be more informative and are going to be treated as more important nodes. This is something that is motivated by the spectral graph theory, and the later chapters of the books will also go over these relationships as well. The main example that motivated the authors in building this is the citations, and let's say a paper here is this node has been cited too many times. So when assuming the connection, when you have the task of the inferring community membership in a graph, these papers are not going to be very informative because they are cited a lot of times at different domains. And they contribute very little to basically reducing the entropy of the task at hand. Then there's the graph convolutional networks, or GCNs, that employ this symmetric normalization in their self-loop approach. And their update rule is this. So you have the neighbors of node u along with the node u itself, so you have a self-loop. And you take the representations and you do divide them by the rule of the symmetric normalization, and basically you have this. And this is one of the most famous and effective approaches in the graph representation learning. Now, a critical question is raised here, and that is whether or not to do normalization. One thing to consider is that when we were talking about like the basic aggregation of sum, that sort of aggregation is more powerful than normalizing the results, because by normalizing the results, it can lead to a loss of information of some sorts. For example, normalizing by the degree, it's going to make it harder or even impossible to kind of tell nodes apart based on their degrees. So it's basically has to do with a lot of things such as numerical stability of the framework that you're proposing and things like that. But it kind of comes back to the application as well. Like if the semantics of the feature vectors associated with the nodes are more important than the structure, normalization is generally a better idea. And if the structure is pretty more important, then maybe more thought is needed. We discussed that being able to represent sets is an important component when it comes to interpreting and discussing and understanding graph neural networks. So in this section, we're going to go over the set aggregators and talk about different types of methodologies that are proposed to do so. Now we know that the aggregation part mainly plays this part in receiving the messages from the neighboring nodes, including possibly the self loop. Now, we discussed the normalizers and normalizations as a possible way of improving them, facing problems such as numerical instabilities. Now, the question is, can we do more than normalization in order to improve the aggregation module in graph neural networks? When we are performing the aggregation, the input to that aggregation is a set, namely, for node U, the input is this. The embedding HVs for all of the V's that are basically nodes of the neighborhood of U. And in the case where the self loop is added, we can have something like that as well, but for the sake of argument, let's just look at this for now. The idea is that basically the input is a set. That means the methodology that works on it, by definition, should be permutation invariance. And we want to turn this into an aggregate message. Let us talk about set pooling. A principled and well approach to defining an aggregator function in the graph neural networks is based on the theory of permutation invariant neural networks. For example, we have this way of approaching this problem. So let's first write the formula. This message, this is neighbors of node U. So we have this MLP here and this MLP here. So you could think of it as a local global approach, which is because of this sum component permutation invariant. And this article has shown that this is a universal approximator for set functions. And MLP means arbitrarily deep multi-layer perceptron. Now, it is also possible to, for example, substitute this summation here with max pooling or min pooling or something like that. And some other works, for example, such as graph sage pooling, has used the normalizations that we discussed earlier instead of this. Now, even though in theory this works and MLPs can be arbitrarily deep, usually in practice it's going to be 1 or 2 layers, and the reason is that the deeper the network, the higher the chances of overfitting, and with a shallow MLP, the risk of overfitting is smaller. Now let's talk about Janusy pooling. Now, in what we had before in the set pooling, we basically were applying a permutation invariant function, and we relied on basically summation or max pooling or min pooling in order to kind of enforce this indifference towards permutation. Now, in Janusy pooling, the situation is a little bit different. This time we consider several permutations, and this time we apply a permutation sensitive function, and then basically kind of average over these latent space representations. So in order to represent that, let's say Pi is a permutation over the set of nodes V. And again, let's consider, for example, a set this. And now applied, basically if Pi is applied on it, we can say it's going to map this set to this. Now what we do here is that in order to compute this, we have an MLP applied, but the input to this MLP is for all of the permutations. And we will discuss that if we consider all of the permutations. Again, in theory, this could be a universal set function approximator. So we take each one of the potential permutations, And then we apply a permutation sensitive function to this, and we basically have the outputs. Now, there is one problem with this, which is basically the fact that, yes, now we have all the possible permutations, and having all possible permutations, as you can imagine, is not always a tractable solution. So there are usually two approaches to kind of deal with this, and one of these approaches is good enough. One approach is to sample a random subset of the permutations and basically use that. This is similar to, for example, negative sampling and things like that, where you sample not everything, but good enough examples. And the other solution is to employ a canonical approach. For example, sort the nodes based on the descending order of their degrees and randomly break the ties and something like that. So these two approaches are basically the main keys in making this methodology tractable. Now, this study has investigated the Janus style pooling and the set pooling and showed that on several synthetic evaluation setups, the Janus style pooling actually has some advantages and shows better improvements upon the previous set pooling based approaches. Now, let's talk about using a tension mechanism in the aggregation layer. And as you can imagine, this is going to be very intuitive and very efficient in many aspects. Now, the first type of GNN models that were proposed to utilize a tension network in this way is proposed in this article, which is called Graph Attention Network, or GATT. And as you can probably imagine, in order to compute NU, we again had this sum. But this time, instead of like naively pooling, we had some alpha UV that basically were a result of applying a tension somehow between U and V times HV. And I kind of showed the affinity of HV towards HU and something like that. Now in this paper, the tensions are defined like this. In this formula, A is a trainable parameters, W is as well. And what you can see here is basically that you have some sort of a softmax over these features that are basically, so you modify the representation of U, and you basically also map the representation of V, concatenate them, and then basically compute the inner product with A, and then do a softmax, and you will get to alpha U and V. That shows somehow how good enough they are. So in order to fuse their relationships, in order to kind of propose a measure of similarity, what you do is that you concatenate the projected features, you do the inner product with A. Another variance of these attentions is basically the bilinear attention model, in which you define the alpha between U and V to be, again, you will have some sort of a softmax. This time you have a bilinear product between the two. And again, you have the softmax form applied. Another form, which is also acceptable, is to have an MLP. And again, you have the softmax again. Just note that the MLP here is expected to output a scalar value. It is also common to use multi-head attention, in which you're going to have again, you're going to have alpha UV HV. This time you're going to have K index as well for each one of the heads. You're going to compute each one of these aggregate messages and have usually a linear projection as well, leaving you with this. And then the message is going to be computed by concatenating the outputs for different heads.